In section 2.2, we talked about permutations. And remember, a permutation is just a way of arranging some set of elements, set of distinct elements. And if we didn't want all those elements, if we only wanted a few, we called that a k permutation of n elements. And we had found that the number of k permutations of n elements, the number of ways to select k items out of a set of n items and arrange them, was given by the formula n factorial over n minus k factorial. That just came from the multiplication principle, where we had n options for the first choice, n minus 1 for the second choice, all the way down the line, and you had a total of k many spots. So this ended up being n factorial over n minus k factorial. In section 2.3, we asked the question, what if we don't really care about the order that you select the elements? What if we just want to count the number of ways to choose k elements out of a set of n elements, but we're not going to arrange them? Right, so let's look at an example. We know from the last section that there's p53, right? There's 5 factorial over 5 minus 3 factorial. Or I guess we should simplify this. 5 factorial over 2 factorial. What's that going to be? This is 120 on top. 5 times 4 times 3 times 2 times 1 is 120. Divided by 2 times 1 is just 2. So there's going to be 60 ways to choose 3 books out of 5 total books and arrange them on a shelf, because that's just a 3 permutation of 5 elements. Another way to see that is by saying we have 5 choices for the first book on the shelf, 4 choices for the second book, having already chosen a first book, and then 3 for the last book on the shelf. So 5 times 4 times 3 gives you that 60 that we're looking for. So now what if I asked, how many ways can we choose 3 books out of 5? How many ways can we just choose them? I don't care about the arrangement anymore. Well, I mean, one way to try to do this is just by thinking through all the different possibilities. You know, you could choose, let's say our books are books A, B, C, D, and E. You could list out all the different ways. You could choose A, B, and C, or A, B, D, or A, B, E, or you could choose A, C, D. A, C, E. Oh boy, I can already see that this is going to be annoying to do. Or A, D, E. I think this is all the choices that use book A. So you could also do B, C, D, B, C, E, B, D, E, or C, D, E. Is this it? Let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think this is all the different ways. So you can double check and see that this is all the different ways that we can choose through the books. But notice, we don't care about the order. So I chose A, B, and C as a possible choice, but I didn't also list A, C, B because I don't care about the order anymore. In this example, all I care about is how many ways can you choose the books, and the arrangement doesn't matter. This is really the same choice of books. You're choosing the same 3 books. I don't care about the order, so I don't want to count that twice. So it's possible to just list out all the different number of ways to do this, but it's definitely tedious. If you had something like 10 books and you wanted to count all the different ways of choosing 5 of them, it's not really useful to do this anymore, right? It doesn't really make sense to try to list out all the different ways. It's too easy to miss one, and there's just too many to list. And so one way of trying to count the number of ways to make this choice is to start with the number of permutations and then just get rid of the duplicates like we did over here. I know that there's 60 permutations, but this number is bigger than the number of choices when we don't care about the order, because we don't want to count all the different ways of arranging A, B, and C, right? I don't want to count A, C, B. I don't want to count B, A, C anymore. Those are really the same choices, and I don't care about the order. So what I can do is I can use division as a way to account for this, right? Each one of these choices of 3 books is going to account for a whole bunch of different permutations of those books. Let me give you an example here, right? How many permutations are there of our first book choice, A, B, and C, right? There's A, B, C, there's A, C, B, there's B, A, C, there's B, C, A, C, A, B, and C, B, A. Okay, oops. there's 6 different permutations of this single choice of 3 books. And so this one combination of books is going to be accounted for 6 times when we look at all the different permutations, right? It gets counted 6 times, or really 5 times too many, right? But it gets counted 6 times instead of just once. Similarly, how many ways could we arrange the choice of books A, B, and D? Well, you could do ADB, you could do DAB, you could do DBA, you could do BAD, or BDA. So just like before, there are 6 permutations, but we really only want to count this as one single combination, one single choice of 3 books where we don't care about the order. Each one of these, right, each one of these 10 choices of books is going to account for 6 different permutations, which makes sense because there should be a total of 60 permutations. And so if we wanted to count the number of combinations, the number of ways to choose 3 books without ordering them, we could start with the number of permutations, that's our 5 factorial over 5 minus 3 factorial, and then divide that number by another factor of 6, because each of these permutations is going to be counted 6 times when we only want it to be counted once. Why is it counted 6 times? Well, because there's 3 times 2 times 1, or 3 factorial, which is equal to 6, many permutations of those 3 books. So this function here is going to tell you the number of combinations, the number of ways to choose 3 books without arranging them. Right? So we say that a combination is just an unordered selection of k elements chosen from a set of n elements. And we use the following formula. So the formula looks like this. The notation is n over k with parentheses around the outside, and we read this as n choose k. Note, this is not a fraction. This isn't n over k. Right? That's not correct. There's no fraction line in the middle. We just stack them right on top of each other, an n over a k. So the number of combinations of k elements chosen from a set of n elements is going to be given by the formula. We'll start with the permutation formula, that's n factorial over n minus k factorial. But then we also want to divide by the number of ways that you can actually permute, right? The number of ways that you can arrange those k elements. Because I don't want to count those as separate combinations, but they're all the same. We're overcounting them here. So I'm going to divide by k factorial to account for all the different ways that you have overcounted those permutations. Right? So the number of combinations is going to be fewer than the number of permutations. Start with the permutation formula, that's n factorial over n minus k factorial, but then divide by k factorial as well. Okay. So let's look at a couple of examples to make sure we understand what this formula is saying. One thing to note, and we talked about this a little bit in the set section, this formula is going to tell you the number of subsets of a particular set of some cardinality. Because remember, we don't care about the order in a set, right? Sets don't have any particular order to them. So if you say had the set A, which consists of all the numbers from 1 to 10, and you wanted to count the number of subsets that have, let's say, cardinality 1, really we're asking how many ways can you choose one element out of this set? Okay, clearly it's 10. I don't really have to do any hard work here. You can either choose the subset which just has a 1, or you can choose a subset that just has a 2, blah, 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 or you can choose a subset that just has a 10. Fine, easy enough. How many subsets of A have cardinality 3? How many subsets of A consist of exactly 3 elements? Well, this is harder. Right, I don't actually want to try to list all of these. I could try off to the side of scratch work. I could pick 1, 2, and 3, or I could choose 1, 2, and 4, or I could choose 1, 2, and 5. I'm already getting tired of doing this. There's going to be a lot. But remember, this is just a selection of 3 elements chosen from a set of 10 elements where the order does not matter. Right, this is the key. When you're looking at sets and subsets, order does not matter. So this is going to be a combination rather than a permutation. And in particular, it's going to be a combination of the form 10 choose 3, because there's 10 elements in the set and we're choosing 3 of them. So the total number of combinations is going to be 10 choose 3. We know from that last formula on the last page that we can get this by doing 10 factorial over 10 minus 3 factorial times 3 factorial. In other words, 10 factorial divided by 7 factorial times 3 factorial. Okay, if you wanted to try to actually list this out, I don't particularly care. I'm fine with you leaving an answer just like this. But if you wanted to simplify this and actually get a number here, 10 factorial is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in the bottom we've got 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we're multiplying that by 3 factorial. So then we have another times 3 times 2 times 1. So this is going to simplify with a lot with cancellation. We've got a common factor of 7, 6, 5, 4, 3, 2, and 1. And then we've got a 3 and a 2 and a 1 down here. So I can sort of take up one of these factors of 3 and one of these factors of 2. And the 1's just a 1, that's fine. So what do we get in the end? We get 10 times 3 times 4, 10 times 12, which is 120. Okay, so that's what we end up getting, 120 subsets. I'm glad I didn't try to list them all. All right, I don't particularly care about the number you get at the end. I really care that you understand what the formula is telling you. So similarly, how many subsets of A have cardinality 7? This is like asking how many ways can you choose 7 elements from this set of 10 elements. Just like before, this is a combination problem because the order does not matter. So this should just be 10 choose 7. That is 10 factorial over 10 minus 7 factorial times 7 factorial. Okay, that's 10 factorial over 3 factorial times 7 factorial. Aha! I don't have to do this work anymore. This is literally the same number as we have up here. Just by the commutative property of multiplication, I've just swapped them around. But this is the same number. This is also going to be equal to 120. But you get this 10 choose 7 here. So there's going to be 120 subsets of cardinality 7. That's maybe a little suspicious, or at least a little interesting that you got the same number for both of these. We'll come back to that. Finally, how many have cardinality at least 7? Ooh, now we have to think a little bit more carefully. At least 7 means how many subsets of A have 7 elements or more? So for this one, I really want to use the addition principle in a way because we're breaking it up into cases. Let's first count the number of subsets that have cardinality 7. Then we'll count the number of subsets that have cardinality 8, or cardinality 9, or cardinality 10. Because if your cardinality is at least 7, that means it's somewhere between 7 and 10. Can't be bigger than 10 because there's only 10 elements in the set to begin with. So using this same idea here, the number of subsets of cardinality 7 is going to be 10 choose 7. The number of subsets of cardinality 8 would be 10 choose 8. The number of subsets of cardinality 9 would be 10 choose 9. And the number of subsets of cardinality 10 is 10 choose 10. If I wanted to write this out with factorials, I could do so. One thing to notice when you're doing these combinations, when you have something like 10 choose 7 and you fill it into this formula, you end up with 10 factorial over 7 factorial and 3 factorial. The two things that are getting factorialed, for lack of a better word, in the bottom should add up to the number being factorialed in the top, right? So this first term is going to give you 10 factorial over 7 factorial, 3 factorial. This next term is going to give you 10 factorial over, okay, what adds up with 8 to give you 10? That would be 2. So it'll be 8 factorial, 2 factorial on the bottom. This is going to be 10 factorial over 9 plus what gives you 10? That would be 1. 9 factorial times 1 factorial. And finally, 10 choose 10. It's a little bit silly, right? How many ways can you choose 10 items out of 10 items? You have to pick them all. There's only one way. But using the formula, this would be, I've run out of space almost, 10 factorial over, here, because I've run out of space, I'm going to do it down here. 10 factorial over 10 minus 10 factorial times 10 factorial. That is 10 factorial, I shouldn't use an equal sign here. over 0 factorial times 10 factorial. This should scare you at first because you never want to have a factor of 0 in the denominator, but just as a quick note, 0 factorial is defined to be equal to 1. Why? How many ways can you arrange 0 items? 1. Just don't arrange them at all. That's sort of a silly way of looking at it, but essentially we want to make sure that, with cancellation, you'd end up with 0 factors of any positive numbers. And so with division, that's just going to give you a 1 there. Okay. So now let's try and extend that to question 2 here, because we had learned in, I believe it was section 1.1 or 1.2, that every subset of a set, especially subsets of a set consisting of natural numbers here, can be coded using a bit string of length, whatever the cardinality of the set is. In other words, the subsets of the numbers 1 through 10 can be coded using a bit string, a binary string with 0s and 1s, of length 10. And just as a reminder, in case we've forgotten how that works, if you had, for example, the bit string 0, 1, 0, 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this, the way that we encode a subset with a bit string is anytime you see a 0, don't include the first element of the set, or don't include that element of the set, and anytime you see a 1, you do include that element of the set. So this says don't include 1, but do include 2. Don't include 3, but do include 4. Don't include 5, 6, 7, 8, or 9. Do include 10. So this bit string is going to encode the subset 2, 4, and 10. What this means is that if we want to count the number of bit strings that have exactly 3 1s, this is one example of that, any bit string that has exactly 3 1s will encode a subset of A. A is our set from the last example. It's going to encode a subset of A that has exactly 3 elements, because a 1 is going to give you an element. In other words, it encodes a subset of A of cardinality 3. Aha, we already answered that question. There's 10, choose 3, or 10 factorial over 7 factorial, 3 factorial, or 120 such subsets. Similarly, a bit string of length 10 with exactly 7 1s, something like 1, 1, 1, 1, 0, 0, 1, 1, 1, 7, 8, 9, 0. This is a bit string with 7 1s. It's going to correspond to the subset. All right, I want a 1, a 2, a 3, and a 4. I don't want 5 or 6. I do want 7, 8, 9. I don't want 10. So it's going to correspond to a subset with exactly 7 elements, because every 1 in the string gives you an element here. So this will encode a subset of A with 7 elements. So if we want to count the number of bit strings of length 10 that contain exactly 7 1s, that's like saying how many subsets of A have exactly 7 elements. Just like before, this is equal to 10, choose 7, which is equal to 120. How many contain at least 7 1s? Well, at least 7 1s means 7 or more 1s, and those subsets are going to have 7 or more elements. So this will encode a subset of A. Right, each one of these bit strings will include a subset of A with 7 or more elements. And we saw in the first question that the number of such subsets is 10, choose 7, plus 10, choose 8, plus 10, choose 9, plus 10, choose 10. All right, whatever number that is. I don't feel like simplifying that, but that's going to give you some number. The same number you got up above. Let's do one last example of combinations. How many ways can you choose 4 out of your 28 friends to ride in your car? You have all these friends, but only 4 of them will fit in your car. How do you choose the 4? Or I guess that's really a personal choice. The question I'm asking is, how many ways could you choose the 4? right? Well, this is a combination, right? Because we don't care the order that we're selecting the friends. If you choose friends A, B, C, and D, or you choose friends D, B, C, and A, it doesn't really make a difference to them. Either way, they all get to go in your car. The order does not matter here. Order does not matter. So this is going to be a combination. In particular, it's a combination of 4 friends chosen from a set of 28 friends. And we know from our formula that this is going to be 28 factorial over 28 minus 4 factorial times 4 factorial. That is 28 factorial over 24 factorial times 4 factorial. I don't really care what that's equal to. It's equal to something. It's a lot of different ways.